Buongiorno. Good morning in Italian. For today's video, we're going to be doing the project of a turntable. I've always wanted one for photography, video work, art things that I've done in the past, and now for 3D scanning and so forth for some of my 3D printing stuff, as well as even potentially for the CNC router. So this particular turntable incorporates features that are helpful for those situations. Primarily one where we can start and stop it at very precise angles, which is good for scanning. Now this project will require 3D printing a number of components. I believe it's sized so that it can be made on most 3D printers. Materials PLA. Of course, I'll include both the step files as well as the STL files on the companion website. Getting started, let's take a look at what we've got here for the main mechanical components. You're going to 3D print a top disc. We're going to 3D print a motor clamp, motor clamp, a drive device, a little clamp to hold one of the circuit boards in place, and then the main base, which has where we mount all our switches and connectors. The top surface is flat. It's not exposed at all. Inside, it's got all the areas where we would put the fasteners for mounting our DC to DC converter, our motor driver, all the other guts that go into a turntable. We're going to start out with the mechanical assembly. And the one thing that you'll want to pay attention to when you're 3D printing is you really want to kind of hold size pretty accurately. And that'll all be starting with the two bearings that you're going to purchase to do this. All these links will be in the description below. Now, these are flanged bearings, and they allow us to connect it together as such, the top and the bottom, and put a little tension on it. But you want these pieces, the bearings, to fit somewhat snugly on the shaft coming out of the back of the turntable, and then in the hole, which is in the base. If you don't have a snug fit there, it's going to flop around and wobble. And that's ideally not really what you want, especially for photography and video work. If you get the holes a little too big, a little nail polish or paint to fill up the gaps, so to speak, will work fine. Just brush some in there, let it dry, and then use some sandpaper to get the fit just right. We're going to start out pressing the bearing in the base, and we'll do the same from the opposite side. Flip it back over. We'll get the disc in there. And that's a nice fit. No wobble, it's not flopping around, not rattling. And that's ideally what you want. We'll turn it back over. And now we're going to start needing some tools. Now, a lot of these fasteners are available. They're kind of tough to get. I buy a lot of fastener kits off of Amazon and eBay. These happen to be, I believe, 3mm screws. Again, that information will be in the description below. So this little device here should, again, fit snug. The diameter of this should fit snugly in the hole in the bottom of the shaft. So we'll drop that in, and we'll tighten those screws up. And and I put a little bit of pressure on those screws. You don't super tighten these. They're compressing the two bearings together, which will then pinch the top surface of the base unit. So we're creating a compression in there on those bearings so that they're not wobbling around. And that's the purpose of having two flange bearings. But now you'll see it spins, but with a little bit of drag to slow it down. And that'll make the operation run much more smoothly, especially that I'm using a stepper motor for this drive mechanism. A lot of times you'll see gear motors used for turntables, but those are hard to give precise angles for starting and stopping when you're scanning something in 3 dimensions. You want that perfect angle. So that feels just about right. Now with all the bits and pieces here, you'll get an idea of the wiring and so forth. Now, traditionally I would do a fritzing diagram, but with this mess and number of components, it seemed to make sense to do a schematic. Unfortunately, I don't have all the symbols anymore due to my server crash a while back, so I had to just put some notations in there where connectors and such go. But we'll take a look at this wiring in detail on the schematic rather than here in the real world. But I just wanted to show you how I did the wiring. I used a lot of DuPont connectors, both pre-made cables, as well as crimping my own connectors, etc. It works out really well for on the Pico, on the motor driver, etc. The rest of the stuff, like this is the connector that goes through the wall. Again, silicone wire. I made up a DuPont connector on that, and then we just pass that through the wall of the base. Here's our remote switch. I purchased a audio cable. It was cheaper to do that than buy a connector and the wire or the cable, so I just bought an audio connector, cut the end off over here, soldered on my momentary switch, my push button switch, put a couple of wire ties on there for a strain relief, and eventually I'll glue these two pieces together like so, and then we'll have it. And of course, being really delicate wires on there, I just broke one off, so I'll have to resolder that back in here before I go for final assembly. So let's take a look at the schematic. This is the whole schematic here. And I've done this in TinyCAD. That's kind of one of my little favorite doodler electronic schematic programs. We're going to be powering this thing with a wall wart, AC to DC wall wart. 9 volt, 2 amp should be more than adequate. The whole system doesn't really draw a lot of current, but I always prefer to favor a little bit on the extra current rating rather than on the max current rating. Otherwise, you'll run into trouble. That'll plug into the base of the unit through a panel connector, which then goes through our DC to DC converter. The DC to DC converter is going to take that 9 volts and drop it down to 5 volts. The one that I picked, again, is 5 amps, way overkill, but no sense in trying to run these extremely inexpensive components at their maximum ratings. Now we'll take a look over here at our trigger switch, which was this guy, the thing that I got to resolder here in a couple of minutes. Momentary switch that'll pass through the base with a panel connector and connect up to ground and GPIO 10. And then a toggle switch, which will be this guy, is going to allow us to select the rotation for clockwise or counterclockwise, and that connects to ground and GPIO 15. For speed, we're going to use a 10K pot, which is this guy, and that will mount right on the base with a hex nut. That'll get power from the Pico, And it'll also use ground from the Pico, and then that feeds back, the wiper feeds back into the analog to digital channel number 2. Down here by the motor, we've got a NEMA 17 stepper motor. This guy here, you've seen these on 3D printers, and based on the brand name of this one, I believe it was sold, or I purchased it off of Amazon, but it's most likely for a 3D printer. Works perfectly for this application, though. That has only 4 wires. It's bipolar. And that's going to go into this TMC2208 stepper driver. It's a very nice stepper driver. It's one of those silent ones. Works out really, really well for this application because it does run very smoothly. But basically, you've got your A and your B windings, and you'll connect those to M1B, M1A, M2A, M2B. If it runs backwards or whatever from your desired way, just reverse the A and the B wiring. So you got 4 wires that go into the driver for that. The power side of the driver here is powered by the 9-volt side of our supply. So you run wires over here and connect those to the TMC 2208 to provide 9 volts of power for the drive side. VIO, voltage in for IO, and ground. That's coming from 3.3 out of the Pico and ground from the Pico. To the other side of it, we're going to start with, let's start with the direction signal. This is the one that going from the Pico to the driver, telling it which way to rotate the motor, clockwise or counterclockwise. The pin for that is labeled DIR on the TMC 2208, and that's coming back to GPIO 16. GPIO 17 is going to go into the step input of the driver. And that's the individual pulses that make the stepper motor move from one rotational position to the next. And then we got a few little other settings that we have here. MS1 and MS2 are used to define the micro-stepping capabilities. So MS2 comes back to GPIO 18, GPIO 19 connects to MS1, and then finally Enable is connected to ground over at the Pico. And that's all of this is described hopefully a little more cleanly on this schematic. So from here, what I got to do is get all these parts in there, and I think we'll just throw some music on and you can kind of watch me fumble through this. The next step here, I'm just taking an extra step because I don't have a very good memory anymore. I've plugged in the power supply. And what I want to do is verify that when I solder these wires onto that connector, I've got polarity correct. So I've just got my multimeter, I've got it plugged in, and I should get 9 volts right there. So that tells me the short terminal is my positive, the long terminal is my negative. Here's our input side where all our switches go. We'll have power going in here. This switch connects here. This controls velocity. This controls direction. And there's a port to access the Pico if you want to reprogram it, or actually once you get it to this point, you'll do your final testing and then you'll save your program in there as a main.py instead of a turntable.py or whatever, so that it automatically runs. So now with that, we're going to start moving on to testing. Moving on to the testing phase now, I have disconnected, let me get the schematic up here. You'll see right here where we normally would power the Pico directly from the internal power supply. I've disconnected that jumper right here. That would be the one up near the wall. And here that is right here. I don't want to power it from an external source while I've got my USB connected to it. I've also now connected up the wall wart power supply so that it's got our 9 volts to operate it. So we'll look at it first from a functional point of view, then we'll dive into the code and then kind of mix it up a little bit. But what you're looking at here, I'm powered up, 9 volts going in, got the code running from Thani. Actually, I just stopped it. We'll get it running again. And now it'll work great for just a rotary table. And it's variable speed, so you can set your velocity or rotational speed with your potentiometer. That works out real well. And we'll put a little helmet on there so it's kind of a little more obvious what's going on. Now, you can reverse the direction. It'll do a little pause in between. And we'll demonstrate that again. Pause and then start rotating. So you can change direction while it's running, and you can control the velocity. And that's, frankly, the bulk of what I'm going to use it for, with the exception of when I start working with it to do scanning of three-dimensional objects, such as helmet here. You can imagine a camera or other scanning device looking at it from one side, and then you'd rotate it, say 5 degrees, stop, rotate it 5 degrees, stop, and take an image, and so forth. So with that, let's dive into the code now and see how this whole thing operates. I'm going to get this back a little bit because I'll need my keyboard. Here we are in the program. At the comments at the beginning, it talks about the operation. Power is on when plugged in. There is no on-off switch. Default operational mode is continuous rotation, just as we demonstrated. Speed of the rotation is controlled by the potentiometer. Direction of rotation is controlled by the toggle switch and can be changed when rotating. If you turn on the device with this connected, your remote switch or trigger, you would be holding the trigger with it plugged in, and now the unit will be in incremental mode, meaning that every time you press the button, it's going to move a preset number of degrees. And then you can force continuous rotation while in incremental mode by holding in the trigger switch. A note here, the pot is wired backwards to give a range such as counterclockwise on the potentiometer will give you 655.35, clockwise would give you 0. That just works out a little easier when you're trying to work on velocity and direction and so forth. Practical results that I got with the 10K pot were 250 a value, ADC value, up to 655.535. And then the range, total range in that operational mode is 65.285. And again, those are analog readings. This particular motor is 200 steps per rotation. We're running it through a step and direction driver. So what we want to do is get the micro steps established. So we're setting it up for 16 micro steps or 3,200 steps per rotation. That'll give you a nice smooth operation. I've included some of the reference data here in the comments, as well as sourcing for different items. Hopefully that will help you. We get into the code now. We're going to import the machine library, and then from that we'll also be importing pin. We're going to import the time, sleep, and sleep microsecond libraries, and we're going to have a thread running doing multitasking to keep things moving along nicely. We're going to establish some pins here. M1 signal is on pin 18, and that configures the stepping mode at 16 microsteps. 2 pins are used to configure it that way, 18 and 19. Now our controlling pins will be our step signal, that single pulse. For every pulse it will move 1 step of the motor. That is on pin 17. We'll set that to 0 for a known state when we get the system up and running. Up here you'll see that I set the value of these signal pins to on state so that we get the 16 microsteps. Changing these to on or off would give you the various configurations of microstepping. Our direction signal, that comes essentially from the toggle switch, and depending on the state of that, I'll either rotate clockwise or counterclockwise. Speed control is calculated based on the reading from the analog to digital converter on GPIO 28, that is our ADC number 2. The trigger switch, this guy, would be connected to pin number 10, and the direction switch is connected to pin number 15. That's the toggle. Steps per degree, these are used in the calculations for a variety of different things to keep velocity and for rotating the table just a specific number of degrees if we're in incremental mode. Degrees per stop, that'll make a little bit more sense. Right now, it's currently set to rotate 10 degrees, stop, 10 degrees, stop, etc. And you could set that to any angle you need. The operational mode by default is continuous rotation. Based on our startup here, this is all startup code. We're going to make a determination of which way the direction switch, the toggle switch, is set to. And we will set the startup rotational direction either clockwise or counterclockwise. We will set the speed delay at 12,000. That's just a preset delay so that the table doesn't turn too fast if initially powered up and your rotary potentiometer is up high. In this section of the code, this is actually not only a function, but it's also a thread. And as you know, threading on the microcontrollers with Pico, or the Pico microcontroller and MicroPython, it is experimental. It has been behaving in a lot of the situations that I'm putting it through, and it is working here. but there are some quirks with it. So our function is table control. We're going to import the time library. Apparently, functions that are in threads need to have the library loaded. We've got a few global variables here as a way to communicate with this function. We've got speed delay, rotational direction. Speed delay comes from calculation off the pot. New rotational direction if we change direction. Operational mode, continuous rotation or incremental. Our step counter, which is used to determine how many degrees to rotate when in incremental. Number of loops, and then test counter. And that's more for debugging. We're going to set up some variable to a default value. Rotational direction to nothing, and loops to 0. Now we're getting into the meat of this function. If the operational mode is continuous rotation, meaning that we powered it up without the switch held on our trigger and without it connected. So we go into an endless loop there. We will test to see if the new rotational direction is not equal to the rotational direction, meaning that it has been changed. We'll sleep for a half a second. We will assign rotational direction to the new rotational direction, and we will change the direction going to the motor driver. We'll change that output signal so that the motor driver now goes the opposite direction. Another test is performed in this loop. If the speed delay is less than 9,990, movement is okay as long as the speed is high enough, meaning the potentiometer is up high enough where there can actually be movement based on the motor torque, etc. We will turn on a step signal, and that's only for 1 microsecond, somewhere between 1 and 3 microseconds seems to be, we'll call it the standard for most drivers. And in this case, 1 microsecond has been working good. Step signal turns back off. So we turn it on for a microsecond, turn it off. That is a pulse or a step signal in this case. We're going to sleep our speed delay. This is the variable that's actually controlling how fast this device will rotate. The longer we wait between steps, the slower it will move. We'll increment our counter, and then if the counter is greater than 3,200, we are going to just change our counter back to 0 and reset our loop counter. And I had a comment in here to show that I was going 360, testing out my microsteps and all my math. Otherwise, while this is running, if nothing has changed, none of the conditions required action, it'll just sleep for a quarter of a second, meaning that most likely the velocity is set low and we don't want it rotating. So it just comes into here, sits there for a quarter of a second, and then comes back to it until finally speed delay is within a range that we can move at. So in other words, if we rotate our potentiometer all the way counterclockwise, the table stops rotating. And then my test counter's incrementing here. Moving into the next section of the code where we're in operational mode, incremental. Step counter gets set to 0. We go into an endless loop here. The step signal value will be turned on. We'll sleep for a second and turn it off. That's our step signal. And then we're going to sleep for our speed delay time. And then we're going to increment our counter. And then this is where it'll make a decision how many steps to make before it's allowed to do, until it stops, and then before it's allowed to start moving again. So if the step counter is greater than the round of the steps per degree times the degrees per stop, if it's moved far enough, we'll wait here until the trigger button, this guy, is pressed. That'll reset the counter, and then it'll exit this loop and go back to making the moves necessary to go the next set number of degrees. And that was set up here, degrees per stop. We'll find it here real quick. Degrees per stop right here. And then currently it's set to go to 10 degrees. So that's how it controls that when we're in incremental mode. And then this loop just continuously runs. We need to take the analog signal and map that into something we can use to perform calculation of time to get our delays between each step so that we control the rotational velocity. And essentially what we're going to do is map that to the number of seconds that we want to work in for our delays. So we map our range of 65,285 to our range of 8,000 in our microseconds of sleep. And then from that, we can take and map our feedback from the potentiometer into a speed delay calculation or a time calculation. And that's what all of this is doing in this area. So every time the analog is changed, this is performed to adjust speed control. We've got a couple of more variables set here before we start running the program. Remember, this is a function, and this is also a function, but also a thread that's running. Now, at the startup, we need to determine whether or not this is plugged in and the switch is held closed. That will put it in incremental mode. If it's not held closed and not plugged in, then it's going to go into continuous operation mode. And that's what this little section right here is doing. If trigger value is equal to 1, meaning that it's open or not connected, thus high, where the switch is pulling it to ground, operational mode is continuous rotation. Then we start our thread up above. If we're in, if the switch is pulled low, the switch is closed, operational mode will be incremental, and then we start the thread up above. We need to get that established before we start the thread up above. And to change from incremental to continuous rotation, you would have to unpower it and then repower it up with the switch held the way you want it. Finally, we get into the operational mode here, where we're running the endless loop in our main endless loop. We're going to get a raw reading from the analog signal. We'll map that to map that analog data so that we have a delay time. We will check our direction, see if the toggle switch has been changed from clockwise to counterclockwise. And this just sets variables that the thread is constantly reading and acting on. And then this one's just slowed down to run at 50 milliseconds, just so that it isn't running wild and hogging all the resources. That's the whole program. So it is a little bit to get over or get through. If you read through it and experiment with it a little bit, I think you'll get it figured out pretty easily. So now let's see how we can get this to operate in incremental mode. I am going to unplug it from the main power, and I'm also going to unplug it from the Pico. I'm going to stop the program, make sure it ain't running. So I'm going to plug in the switch. The switch is plugged in. I am going to plug in, hold the button down, plug in the motor, plug in the Pico, and now is when I'm going to hit run. And now, as we look down below here, starting the run, operational mode is incremental. So now when I press this button, it'll rotate 10 degrees and stop. We'll get helmet on there and send him for a little ride. Now, as you can see, that works out really well for doing scanning and taking photographs of something at different angles, very precise angles. And that's why I designed it this way with a stepper motor and, of course, using the Pico. So we got the ultimate in control of our turntable. Now, also, keep in mind that here I'm using a mechanical switch. I could have another microcontroller operating a camera, and instead of having a switch here, that microcontroller can be controlling this turntable as well. So I could have it completely automated with no intervention at all to do this scanning. So that pretty well wraps up this project called my turntable, and I look forward to using it. You folks have probably already seen it back here on the desk behind me, showing off some of the future projects or other devices on it. And it's going to get a lot of use in future episodes of Making Stuff with Chris DeHut. Well, thanks for watching. I hope that you build one of these for your photography needs or whatever needs you may have, perhaps displaying some cool things around your home that you want spinning on a dial. Thanks again for watching. I look forward to seeing you in the next episode.